Hello everybody, it's lab number 7. It's called the Law of Conservation of Energy. So I've got some fake little GIFs here that illustrate pure conservative forces. So the only conservative forces acting in the system, which means it basically would go on forever. But as we know in real life, things do not, even when they look like they're going on forever, they just slowly end their course and they lose all their energy. Now you know there's this thing called the Law of Conservation of Energy, and it applies to every situation. But the problem is when the conversion takes place, so the statement is energy cannot be created nor destroyed, but merely transformed from one form to another. Well, when it gets transformed into what's called a non-conservative force, when it's removed by a non-conservative force, it leaves the system. And the biggest culprit is friction. Friction's one of the biggest removers of energy from what looks like a conservative system. So like if you went to the amusement park and went on a roller coaster, that thing should actually just, you just stand there all day long. We let you go at a particular height. We give you all this energy, and that energy turns into motion and then back into potential energy, and you should actually be able to get right back to where you started. And when you get there, everything will be back to what it was when you first started. But that's not what happens in the real world because of what's called non-conservative forces, which is basically friction. So this middle one right here, this guy shakes the ball, he gets things moving, and so basically the only force acting on it right now is gravity, but there's also rubbing going on with the glass, and so it just loses that state and ends up as a pile of marbles at the bottom of the ball. Okay, so two of the conservative type forces we're going to be looking at is gravity. So we have gravity right here, and a really good example of a system that looks like it's conserving energy is a pendulum. So you pull it off to the side and let go, and it'll swing back and forth for quite some time, but again, it'll eventually damp out, they call it, damp. It'll damp out and lose its energy. The other one is a spring. So the spring force, which is called Hooke's law, is a conservative force. And it would go on forever if there wasn't heat generated in each little coil of wire as it was stretched and compressed. And also remember, all these things are going through air, and air is drag, and that'll take the energy out of the system, because that again is a non-conservative force. Okay, so that's it. Now we're going to do some math. Now, to begin with, and this is a topic that's pretty old. This goes before even Newton, and it's called work. Work. So some fellow before Newton, I believe it was Coriolis. He's the guy who came up with the Coriolis force. Talk about a non-conservative force. But he came up with the notion of work. And work is done whenever an object is forced through a distance. Whenever an object is forced through a distance. Okay? Now, like I'm holding this pointer in my hand, I'm not doing any work because I'm not forcing it through a distance. Now, there's forces acting, but no work is being done. Now, if I walk with this thing at constant speed like that, I'm still not doing any work whatsoever because the displacement is this way, but the force I'm supplying, which is the normal force in my hand, is this way, 90 degrees. So no work is done. The force has actually got to be in the same direction or opposite the direction for there to be work. Now, if it's in the same direction, it'd be positive work. And if it's in the opposite direction, negative work. So imagine you're in your car and you're driving at a high rate of speed and you take your foot off the gas. Well, if you watch your speedometer, it's going to start going woo like that. And it's because the air against your car is producing a force going opposite your displacement and taking away what's called the kinetic energy of your car. Okay? So now, what if you have a force that's applied at some weird angle? So like I'm mowing the lawn. So I got a lawnmower, okay, it's got its wheels here. And when I push on a lawnmower, I push like that. But you see, the lawnmower only moves along this direction right there. So part of the force here, the force it's pushing down into the ground, and if we take this to be the angle theta right here, this is F cosine theta. Oh, hang on one second. Cosine theta. And this over here is F sine of theta. So in this direction right here, there's no displacement going on, so no work from that force right there. No work is done at all. But in this direction here, that will produce work. So F cosine theta, which would be the x component of the force, which is in the same direction as the displacement of the lawnmower, that is doing work. And you know, whenever you cut the lawn, if you've ever done that before, the lawnmower pretty much goes at constant speed, and that's because against your lawnmower is the roughness of the grass, which is providing friction as you wheel the lawnmower through the grass. And you see that force is opposite the displacement, so this is doing negative work. So there's no net work being done. You're supplying the force to move it forward, and friction is stealing away all of that energy that you're putting into it and turning it into heat and light. So your grass not only looks good, it is hot. Hot grass. Hot grass. Okay, so here's how you calculate work. So work is the vector F dotted scalar product into the displacement. Now if the force is not a nice force, you have to do an integral if the force is changing over the displacement. But if the force is constant, like gravity, you can just yank that out of the integral, and then the integral is super easy. So anyway, when you do the dot, remember you got to do cosine theta. So you learned that in your Calc 2 class. The scalar product is the two vectors times the cosine of the angle between them. Okay? So for instance, over here, you see this is the displacement delta x, and this is the force like that. And so you see when I do cosine of theta, that gives me fx. So f cosine theta is fx. So that's a scalar product. So only work is done when there's a force in the direction or against the direction of motion. When it's with it, it's positive. When it's against it, it's negative. Okay. Now, let's do it for gravity. What if I lift an object up or I lower an object? So this guy's lifting a weight, and when I looked this up online, they're showing me different ways to lift things safely. So this guy's lifting a very heavy bucket, I guess, and he's doing it safely. So it was on the ground, and he lifted it up. Now, if he were to lower this thing, he would force, he'd have to hold on to it, otherwise it would just go crashing to the ground. And so his force would be up, and then the displacement would be down. If he's lifting it, then the force is up, and the displacement is up. So in one case it would be cosine 0 degrees, in the other case of lowering it would be cosine 180. So you can see the work done is either positive if you're lifting, or it's negative. Now remember, W comes out because it's constant. The weight of the bucket is constant. So all you have to do is integrate a whole bunch of little dx's and put a plus or minus sign, and you get your result. So the work done by lifting against gravity or lowering against gravity is plus or minus mg delta h. And we're not accelerating. We're just lowering it nice and easy, lifting it nice and easy. All right, what if we do a spring? Well, a spring depends on position. So the more you stretch a spring, the more force there is. So you have to do an integral. And the force law is called Hooke's law. And so it's K times X. And we want to know how much is it, what's the work it take to stretch or compress a spring. All right, now watch this. So I stretch it. I pull to the right, the displacement is to the right. I compress it. I push to the left, the displacement's to the left. So they're both cosine 0 degrees. All right, so there's cosine 0, and when I integrate that thing, I get 1/2 kx squared. If I start from 0, and I compress it a distance x, or I compress it a distance x. Compression would be a negative x, and positive x would be the other direction. But notice it's x squared, so whether I put a plus or minus sign in there, I get a positive result. Okay. Notice, law of conservation of energy. If there's no non-conservative forces, you see it just goes forever. This has been going on the whole time I've been teaching. Amazing. It's hard to get those perfect springs, but for me, the expense is not too large for you guys. I go out and I get those perfect springs and use them in my lectures. Boom. All right. Now let's talk about conservative forces. So work done against a conservative force like gravity is stored as potential energy. All right? So when you do work against a conservative force, you can actually store it as potential energy. Like this. So I do work on this thing, and it's now stored as potential energy. You see? When I let go of it, you see it wasn't moving when it was down here. See that? I lifted it up, and I stored it as potential energy. Boom! And you see it hit my hand with a certain speed. Okay? That is a conservative force. Now, if I were like pulling this through molasses, the molasses would be stealing all the energy away. When I let go of it now, even though gravity's pulling it down, guess what? Molasses is going to take all of it away. It's just going to go like this, ever so slowly down until it gets to the bottom. Okay, so you won't get that return that you get when you're dealing with a conservative force. All right. A conservative force is a force that conserves energy. Consequence of that, the total work done to move an object between 2 points does not depend on the path. And if the path is closed, then the net work would be 0. So if I take this thing up, lift it up like this, and then I bring it back down here, the net work was 0. By the way, if I lift this up like this, it takes the same amount of work as it does like that. Because there's no forces in the x direction. Okay? No forces in the x direction. So if I want to go this high, it's going to take about the same amount of work. So I take a ball, and I take the ball, and I throw it up into the air. Okay? And it rises up 50 feet. Well, the amount of energy it took for it to go 50 feet up would be exactly the same amount of energy if I were to throw it up just like that, up 50 feet. It doesn't matter that it reached that 50-foot point way down range there. So remember, in the x direction, there's no forces going on. There's no forces whatsoever. So it's just moving at constant speed. So it doesn't matter what path you follow. The same amount of energy, it takes the same amount of work to get to that same level due to gravity. Okay? And it gets stored in there, and then when it gets to the top, it unloads that and comes down. And that's why we had a parabola that was perfectly symmetric. Okay. All right. So now, the potential energy is minus the work we do, okay, to store that energy. So when we do work against gravity, it gets stored as positive potential energy. Gravity does negative work. So when I lift this thing, I'm doing positive work. See, the force is up, the displacement's up. Gravity's doing negative work because the weight is down, but the displacement's up. So that amount of work that gravity does, negative, gets stored as potential energy. So how do you get energy stored? You need an outside force, like me, to do that. Okay? But we have planets that are like in highly elliptical orbits, like Pluto. Well, at some points in its orbits, it's closest to the sun. It's going really fast. Okay? Then it goes around and comes back out. Then it gets further and further from the sun. And so that kinetic energy gets stored as potential energy, and then it gets to its furthest point, and it's going slowest and it's furthest, and then what does it do? It repeats that motion again. It loses the potential energy, and it goes into kinetic energy. And you know, that's been going on for about 4.7, 4.8 billion years. Amazing, huh? Our planet's been orbiting the sun for that long. It's because of space. See, there's no friction in outer space. It's basically empty. All right. Anyway, the spring potential energy is equal to, see if we go back, see the formula right there? See the work? 1/2 kx squared. And for gravity, mgh. And so all we do is we put a minus sign on there. And so now when you lift something, you get positive potential energy. Remember, gravity does negative work. So you get positive potential energy. If something falls, it loses potential energy, and gravity does positive work. So when I let go of this thing, see? Gravity, force down, displacement down, positive, and it's losing potential energy. Okay? This would be between 2 points on a spring. So when you stretch a spring, you do positive work. Gravity, the spring does negative work, 1/2 kx squared. And when you let go of it, you want to know how much potential energy it has here versus here. You have to do 1/2 kx squared for the first position minus 1/2 kx squared for the second position. Up here, delta H, H2 minus H1. That takes care of the minus signs. That takes care of the minus signs. All right, and then lastly, the work energy theorem says if work is done by a net force, it'll change the kinetic energy of the object. Now that proof is kind of fun. So work by a net force. Okay, so if I let go of this thing, there's now a net force. So gravity is doing work, making this thing speed up faster and faster. Okay, so when you have a net force, you're going to dot it into the displacement vector, and you get F net cosine theta dx. All right, now F net cosine theta is the x component of the force, like we talked about before. So that's F net x dx. All right, now F net x equals max, the x component of the acceleration. So I'm going to substitute for F net equals ma in the x direction right here. So F net x is F equals ma, so F net x is max dx. Now, remember, acceleration is dv dt. So this would be the change in the velocity in the x direction per delta t. All right. And I got my dx right here. And I'm going to do a little presto changeo because dx dt is vx. Okay, and you see the dvx? I'm going to put that right there. So that's called the chain rule. All right, and now I can integrate that thing, and you see you get the change in kinetic energy, which is 1/2 mv squared of the second speed minus 1/2 mv squared of the first speed. And so it's called the work energy theorem. And so this is how it's written. Kinetic energy, 1/2 m v2 squared minus 1/2 m v1 squared. Change in kinetic energy. So when you have a net force acting on an object, the work that net force does leads to a change in kinetic energy. Guess what? That's it. All right, so that's the theoretical part. So we're actually going to study that in the lab. Now, you know, you only have 1 hour to collect data. And if you do both experiments, and you really want to aim for both experiments, if you don't get the second experiment totally done, just try to get as many measurements as you can. You really want to get that first experiment done. But before you can do either experiment, you have to measure the spring constant of the spring. So we're going to use a spring to launch a cart down a track. The track will be flat at first, so the net force of the spring is going to change the kinetic energy of the cart. Then we're going to tilt the track and shoot the cart up the track and see how much potential energy we get. That might not get done, but we're going to try our best to see if we can get both experiments done. Okay? So that's the end of the background on the law of conservation of energy. So a big over and out, and we'll see you for the experiment.